Okay, it's 5:01, so I'm going to start us off. Hi, everybody. I am Dr. Star Sparrow. I'm in the Department of Geography, Environment, and Sustainability, and I'm in charge of the Global Environmental Speaker Series this semester. I am so excited to welcome Dr. Chelsea Parker to campus. Chelsea has a bachelor's in science and physical geography from the University of Bristol, a master's of geologic science from Brown University, and a PhD in earth, environmental, and planetary science from Brown University. She is now a research scientist at NASA's Goddard Space Flight Center, NASA Goddard. Also, she contains multitudes. She's a she's a rescue diver. She's a soprano in the city choir of Washington, and she's like actually a terrifyingly good alpine skier. So let's welcome. No, but it's okay. So yeah, just welcome Chelsea.
So yeah, thanks for having me and thanks for the introduction. My name is Chelsea Parker. I'm a research scientist at NASA Goddard and the University of Maryland. So today I want to talk to you about how sea ice is changing. Is it too long?
No, it's fine.
Okay.
The sound is good. Or no? You can say no. Oh, can we turn the lights down? Yes, a little bit. I'm looking at our tech, right? There's a camera. It's being recorded, so it's like. How bad is that?
But it's
okay?
this one instead of that.
Okay, I'm finding it. No. There's a lot of switches back there. Okay.
Not that one. I actually need that to see your face.
Well, can you want to put this one back on?
Hold on. People can just listen to the words. So she's a beautiful video. Is that okay? Okay.
Okay. So today I want to talk about how Arctic sea ice is changing and how the Arctic may be changing into the future, from both climate scales down to synoptic weather scales. So I'm going to set the scene and get us all on the same page. And so I want to cover what sea ice is, why it matters, and how it's changing. So sea ice specifically is frozen seawater that covers ocean surfaces in the polar regions. Where does it grow in the Arctic? So sea ice can grow in these colored regions of the Arctic. And we do often separate by these colors, so different basins, in our analyses because they have quite different characteristics. You will see this North Pole stereographic map a lot over the next hour. So yeah, here's Greenland, here's the top of Norway, North America, Alaska, Russian side. Okay. So sea ice grows over the winter to a maximum, which we see in March. And then it melts over the spring and summer with the absorption of energy, and it reaches a minimum in mid-September before the waning sunlight initiates transition to freeze up again. So it's important to realize that sea ice is a complex and heterogeneous surface over space and time. It's not just one smooth slab of ice that sits neatly on top of the ocean. So in this picture, you can see that the ice is broken up with some rougher areas and some smooth surfaces. But you can also start to see that the ice extends below the surface here. So broadly, this diagram, I want to show that yes, the sea ice is sitting on top of the ocean, but it extends well below the surface. And then on top of the ice, there can be snow cover, or it can be bare, or it can also have melt ponds. So that's surface melt, but there's still thick ice beneath. So just from our visual perspective, sea ice can look like this. So it's very thick and consolidated ice where there's been lots of compaction and deformation of the sea ice. And so it's rough and has lots of ridged surfaces. Sea ice can look like this. So this is still a continuous frozen surface of sea ice that you can walk across, but the surface is beginning to melt, creating these ponds. But yeah, you can still walk through these ponds and cross over for, as you can see, field work. But then you can get to these kind of images where ice is broken up with fractures and lead, so then we see more individualized ice flows and areas of open water. So I'm just going to go over definitions so that we understand everything for the rest of this talk. So sea ice extent is the total area covered by at least 15% of sea ice. So this is the example of what sea ice extent would look like. So we're saying this whole area is covered by sea ice. But actually within that, there's sea ice concentration. So the percentage of a given area or grid cell that's covered by sea ice. So this can range from the 15% to 100%. So you can see there's actually a lot of variation. So then sea ice area we calculate by the concentration times the total grid cell area. So these measures are all in kind of this XY direction. So in this, if we say this is a grid cell, I would say it's roughly covered by 70% of sea ice, but this would be considered that the full area is covered if we were talking about extent. So these are in XY axes. But then in the Z-axis is the depth of the frozen ocean water. So as we talked about, this can extend below the surface. Things I'll talk about is something called first-year ice. So that's sea ice that freezes up in the winter, but it melts out in the summer. Whereas multi-year ice, the sea ice persists through the summer melt season. Surface albedo is something that will come up a lot. So that's the amount of incoming solar radiation that can be reflected by the surface back out into space. So why is sea ice important? It's really important across multiple scales. So on the local regional scale, it's crucial for local ecosystems and productivity. You can see a nice diagram of the pretty active food web in the Arctic region. And at those local scales too, it's important for traditional transit routes and subsistence for local communities. On the broader scale, so across the Arctic, sea ice determines shipping routes, socioeconomic activities, and resource availability. But the local Arctic climate is also affected in terms of when sea ice is changing, the immediate temperature and humidity in the atmosphere can change, but also from the albedo feedback and Arctic amplification, which I will expand on later. So the changes in Arctic sea ice cover also have a far-reaching effect globally, so on the global ocean and atmospheric temperatures, and teleconnections to weather patterns that we experience here and other areas in the mid-latitudes. Okay. So yeah, we can see in this second picture the idea of what vessels can transit the Arctic. So that's heavily determined by the sea ice concentration and the thickness of the ice. And then here, yeah, I'm starting to depict the albedo, so the amount of the incoming solar radiation that can be reflected by the bright surface. So obviously sea ice is a bright surface and reflects back 60%. But I think something that's often missed is that snow is an even brighter surface and reflects almost all the incoming solar radiation back out into the atmosphere. Whereas, of course, the darker ocean surface will absorb most of this incoming radiation and only can reflect a little bit. Okay, so how is Arctic sea ice changing so far? We've kind of talked on and established the complexity and importance of sea ice. But the sea ice cover and thickness are subject to a number of forcings. So forcings from the atmosphere and the ocean. So things like wind and ocean currents and waves drive sea ice dynamics, so sea ice moving around. But then the atmosphere and ocean temperatures and other fluxes like the radiation we've been introducing. So these drive thermodynamic changes, so melting and growth of the ice. But all components of the Earth system are connected. So as I mentioned in the last slide, sea ice conditions then affect back into the ocean and the atmosphere. Okay. So, okay, what we're looking at here is a visualization of the observed sea ice cover at its September minimum and how it's changing from year to year since 1979. Overlain is the extent plotted for you in the numbers. So I hope you can see that there's a lot of variability, but we're also, what should be becoming clear is the long-term trend of significant sea ice loss. So now we're left with a much smaller area covered by sea ice by the end of the melt season. And this trend is in concert with rising global atmosphere and ocean temperatures. So this is what we got right now. Okay. But there's more to it than just what the atmospheric temperature is. So the Arctic is actually warming 4 times faster than the global average. So why is this? I introduced this graphic earlier, but a big player is this albedo feedback loop. So in equilibrium state, the sea ice balances the amount of radiation incoming as the bright surface reflects a significant portion back out. But when we're having warmer temperatures, incoming solar radiation, which is causing ice melt and retreat, and we have a reduction in the snow cover. So in this image, the snow cover is now gone. So more incoming energy is absorbed into the darker ice surface, but also this much bigger area of ocean that's uncovered now. So this warming of the ocean can then further cause melting of the ice from the bottom, but also the sides, so lateral melt. But it also warms the atmosphere back up, so leading to further surface melt, and the cycle continues. So this is a very specific feedback loop that's happening. While this albedo feedback is kind of the main thing we talk about in terms of accelerated warming, there are other feedbacks. So sea ice can increase cloudy conditions, but the clouds can act as an umbrella, so reflecting the incoming solar radiation back out, or it can act as a blanket, so trapping outgoing long-wave radiation, so re-releasing heat. We can't release heat back out. So that's kind of a balance in terms of the feedback loop from that, and it's something that we look into a lot and try and kind of pin down. As water vapor increases in the atmosphere with kind of the rising temperatures that can hold more vapor, and also the ocean open ocean, so we're having a much bigger source of water into the atmosphere. So this reflects the long-wave radiation back down, and so that with the lapse rate feedback, so we again have this positive feedback loop resulting in more melt. So together, these feedbacks accelerate Arctic warming and sea ice loss, and we call this Arctic amplification. So we saw from the animation that sea ice has been changing, certainly since 1980. And we've recently been analyzing the rate of change over time and whether sea ice loss has been consistent in the last 45 years or so. So this is similar to the graph from earlier, but from satellite passive microwave retrievals, we calculate the sea ice area and we find that sea ice is declining. But if you look at the time series more closely, change point detection reveals that there are kind of turning points during this time series. So kind of 1997, there was kind of a short transition here, and then this important transition in 2013. So if we focus on these change points, we see significantly different phases of sea ice loss. So at the beginning of the record, in orange, the sea ice is declining, but the significance is relatively low. But in the green, we see a very steep slope of declining sea ice, and it's declining over 3.5 times faster than in the 80s into the early 90s. And the trend is highly significant. But since 2013, there's a really distinctly different phase. There's still much less ice. You can see that we're still in these low anomalies, but now the rate of change is much slower. These phases have been coined kind of the old Arctic, where the large consolidated ice pack was slowly shrinking, but this kind of rapid transition phase where we had rapid ice loss. And now we say that we're in a new Arctic. So the sea ice cover is reduced, and it's mostly comprised of thinner and younger ice with less snow on top. But based on these trends, it could be considered stable in this new state. So here I'm showing it spatially. So this is the rate of the sea ice loss, so losses in the blue colors, per year during that transition phase compared to what we're seeing in the new Arctic. There are areas of growth where you see the red, especially around Greenland. That's the ice being forced together, so compaction, and that actually increases sea ice concentration. So it's very important to kind of differentiate dynamics of sea ice and thermodynamics. So we see these distinct phases across many measures of Arctic sea ice change. Here I'm showing the rate of increase in the melt season length. So that's the amount of time between the start of continuous melt to the start of continuous freeze up. And you can see that this has increased by over a month since the 1980s. So we have a much longer period of time for ice to be melting. And again, I broke this up into the different phases. So yeah, the green transition, the melt season's increasing by over 2 days a year, but the rate of change has come right down in the blue in the new Arctic. Oh yeah, so this is the spatial plot again. So we've seen the sea ice concentration one, and now I'm showing this melt season length. We see very strong lengthening, so the deep red colors, primarily around the peripheral seas. And in the new Arctic, it's a pretty patchy rate of change. But there is even some shortening of the melt season length, the light blue colors. So hopefully I've shown that sea ice loss has not been consistent over time, but what drives rapid change versus stability? I just want to remind us that the sea ice ocean system is highly connected, and so-called drivers can be hard to disentangle. So this is the same sea ice concentration rates of change, but here is the rate of change in the surface temperatures. So we see rapid warming in the red colors, and especially in the same regions as the rapid ice loss. So temperature could be the driving factor leading to melt. But in the new Arctic, I think one thing I want to stress is that we're still in a reduced sea ice state. So the average sea ice concentration is still actually lower than in the transition period, but it's the rate of change and loss that are much reduced. So if we look further up into the atmosphere, so this warming is also reflected in the temperatures higher up in the atmosphere, in the red. So you could say that likely that climate change with a warming climate overall is causing sea ice loss in this transition period. But we know we're still warming the atmosphere, and you can still see warming in the upper atmosphere in this new Arctic state. But obviously the difference is not quite as strong. But this suggests that it's more of a surface change and feedback mechanism going on in the transition period. So one way we tease this apart is by looking at the surface energy budget and the kind of components of this. So we calculate the energy at the surface by adding incoming shortwave and longwave and subtracting the outgoing shortwave and longwave. So when you have positive values in this calculation, that means there's an energy forcing onto the surface, causing warming and probably melt. Negative values would mean the surface ice is losing energy to the atmosphere, so it would be cooling, and it could help with freeze up of the ice. So again, using satellite retrievals, we calculate the surface energy budget. So I'm showing the rate of change in the daily average surface energy budget during the summer season. And where you can see the hatching, yes, that shows the significance of the trend. So you can see that obviously it was rapidly increasing in the transition period, especially in this Beaufort and Central Arctic and the Canadian archipelago. So over the course of the summer, having that amount of increase on the average of days means that there's a large amount of energy absorption by the end of the season. In the new Arctic, we do still have this higher average surface energy budget, but there's actually some reduction. So the trend is decreasing over time. So these are like the blue patches. So when we examine each of the flux terms, we saw that the net forcing at the surface was largely driven by changing shortwave radiation. And so we had daily increases of 1.3 watts per meter squared per year. But interestingly, again, the average daily surface shortwave flux is actually declining in the new Arctic. So let's talk about albedo again. So I'm showing the rate of change in the daily albedo. So it's a fraction, but I've converted it to percent here just for ease of understanding. So green and blue shows declining albedo as the surface melts and sea ice cover is lost. And so, as we said, it can't reflect as much solar radiation out. But in the new Arctic, the average albedo is much lower, but there is actually some increase in surface albedo, suggesting some regrowth or re-establishment of the snowpack. We didn't just see strong differences in the albedo, however, and this is key. So between the two phases, clouds are playing an important role. In the transition, we actually saw a decline. So the green colors were significant declines in cloud cover. So really on this western half of the Arctic. And there's a pretty apparent flip-flop in the new Arctic with increasing cloud cover. And this is interesting because it's a non-uniform then feedback of what this sea ice cover is and how it's affecting clouds. And then it also shows that kind of there are other oscillations at play. So large-scale oscillations like the Arctic Oscillation and the Arctic Dipole can affect cloud cover in this kind of broad way. So yeah, transition, we had albedo and cloud cover decline and decreased amount of radiation reflected, and so more incoming. And so this really was an albedo feedback, but really enhanced by this cloud cover change. But then in the new Arctic, there are some increases in albedo, but then a pretty significant increase in cloud cover. So now we're increasing what's reflected, and so there's an overall reduction in the incoming shortwave radiation. An important driver, other than thinking about clouds too, is the differing phases of the ice types that we have. So in the transition period, we saw rapid decline of both first year, so that's in the red, and multi-year, which is in black, ice, leading to near zero concentrations of first year ice by the end of each melt season. So now in the new Arctic, this is kind of the new normal. So first year ice now always melts out, and the remaining multi-year ice is much lower, but it's relatively stable. So this explains why some of the rates of change are smaller and less significant now in the new Arctic. But my takeaway is not that we're good and sea ice is not changing anymore, because we know the world is still warming. So this kind of leads us to a question of, will there be another tipping point to trigger rapid loss of this remaining multi-year ice? So an important point is that we've mostly been discussing sea ice extent, sea ice concentration, and sea ice area. So that's what's going on the surface. And so now we have a relatively stable amount of multi-year ice. However, this ice is thinning. So with the continued atmospheric and ocean temperatures, you can see in these red colors here of the January thickness anomaly, we're actually seeing a thinning multi-year ice pack in recent years. So as the remaining multi-year ice continues to thin, it will become more vulnerable to atmosphere and ocean forcing, reaching a point where rapid sea ice loss may be triggered again. Okay, so we've been talking quite broadly about atmosphere and ocean forcings, but what are other forcings that are superposed on top of kind of average climate change that can affect sea ice change and or, lead to kind of a trigger point or rapid or stable conditions? So some such forcings are extreme weather. So let's explore what they are, how they interact with the sea ice, and how they are changing. So polar extreme events include things like cold or warm air outbreaks, intense hurricane-like storms called polar lows, broader, bigger scale Arctic cyclones, and atmospheric rivers. So here you can see a satellite image of a cyclone system. You see the spiral pattern of the clouds. And here's a depiction of an atmospheric river. So these are long plumes of extreme integrated water vapor transport into the Arctic. So this is showing the total precipitable water anomaly, and it's during an event that entered the Arctic over Alaska here. So these weather events, they bring heat and moisture into the Arctic and changes in fluxes, so a lot of the fluxes we've been talking about. They have strong winds and heavy precipitation. So then they can cause both thermodynamic and dynamic changes in the sea ice. And together, a lot of these changes occur at once, and it can have significant effects for local communities and ecosystems and activities there. So in terms of interactions, so the important effects on the sea ice and the ocean surface in this top-down forcing of weather. So as I said, kind of winds induce the dynamic changes, and then we have thermodynamic changes, and importantly, an altering of the snowpack. So precipitation from these events can either add to the snowpack or actually act to reduce it, depending on whether they're raining or snowing, and also depending on kind of the fluxes they're bringing and warm temperatures. So these are all important factors for the overall sea ice mass balance and the survivability of sea ice. But we know that things are coupled in the Earth, so the changing climate and sea ice conditions can alter then the surface atmosphere coupling, and gradients and fluxes, and large-scale flow in this like bottom-up direction. Okay, so how do they affect sea ice? Recent work has shown that sea ice concentration anomalies are significantly associated with atmospheric rivers. So this was a study over winter months. Blue colors show losses of more than 15% during AR events. Okay, and on the right here, we see these dashed vertical lines are when the atmospheric river arrives at the sea ice. So at the top, we can see that they bring increased water vapor in the atmosphere, and then the sea ice area is declining in this dashed red line. So the ARs are associated with increasing downwelling long-wave radiation and a cloud radiative effect. So that's the effect of the clouds warming the surface. And so the atmospheric rivers are bringing significant precipitation. How have they changed in recent history? So I'll just show both cyclones and ARs so that you can understand how this is kind of universal to extreme weather. But this figure shows the average number of strong Arctic cyclones. And on top is the winter, and on the bottom is summer. And so we also see the difference between the more recent years, and the historical years. And so we see an increase in frequency of Arctic cyclones pretty much across the whole Arctic, but with significant hotspots, whether it's in the North Atlantic Passageway or the Central Arctic. This figure shows the trend in cyclone activity index. So this index takes into account number of cyclones and how long the cyclones last, but it also includes sea level pressure anomalies and the horizontal gradient of sea level pressure. So therefore it captures a measure of intensity and geostrophic wind. So you can see that its activity and intensity have also been increasing. This analysis used 3 different data sets, which gives us good confidence in this trend. Similarly, atmospheric rivers have been increasing in frequency. So you can see these teal colors on the top left here. But then there's also a significant increase in water vapor across the whole Arctic. All the dots are significant everywhere. And we have increasing frequency of ARs in the Atlantic sector. So that's from this red sector here, and that equates to this top line. And in the Pacific sector, the increase is shown in these dashed lines down here. Again, it's more than one data set, so we have pretty good confidence. I think importantly to what we've talked about a lot in terms of the surface energy budget is increased accumulated long wave downwelling anomalies associated with atmospheric rivers and increasing rainfall. So rainfall on sea ice can trigger melt of the snow or the ice and significantly reduces surface albedo. Okay, so we know how they've changed, but what are they going to do from here? While we do have insights from global model projections, the resolution and relatively low complexity of global models can often be insufficient to accurately capture short-lived and complex features of extreme weather. So this figure shows the average cyclone tracks from 1950 to 2014. And these are from EROT 5 reanalyses. And we see that there's a significant underestimation of cyclones. So these blue colors show that multi-model ensemble, so that's MME here, of low resolution models, so LR, that participated in CMIP6. So CMIP6 is a really big project. It's the climate model intercomparison project, which gives us great insight of differences between models, but also projections into the future. So we see significant underestimation in the number of cyclones that we can resolve in climate models. There is some improvement in the bias when we go to higher resolutions, but there's still underestimation. But it does highlight the importance of resolution and model complexity. So while I do work in global climate modeling, for extremes, I've been using a regional modeling approach. So what I mean by that is you can use models to effectively zoom in on the Arctic and even subregions. And so you can effectively run simulations at much higher resolutions compared to global models. And you have more frequent output. So you can get 30 minutes, like data every 30 minutes compared to at best from global models, it's like a daily average. So with regional models, we can look at shorter timescales than climate scales. So we can use more sophisticated physics schemes. So in theory, a better representation of atmospheric processes than we can in global models. So you can resolve more features, and with the fine output times, you can really examine kind of dynamics and thermodynamic interaction over the life cycle of a cyclone or an atmospheric river. It really provides a flexibility and a powerful tool to kind of do experiments and explore kind of a lot of science questions and perturbations. So this is an example of kind of a regional setup using the NCAR weather research and forecasting model. So I configured this domain to simulate Arctic cyclones. The tracks are on the right here. But like I said, it's flexible. So I configured this different setup for examining atmospheric rivers. So we have now a pan-Arctic domain, and there's a smaller inner nest, which is very high resolution, to really examine fine scale processes in there. We do need this broader domain so that we can look at atmospheric rivers because they intrude into the Arctic. So this is some results from our simulations. So I'm showing the total precipitable water. And so you can see its output every hour throughout the simulation. And so you can see, hopefully, that the elevated areas of water vapor and transport are in the red colors, and they kind of skirt around the Arctic a lot of the time, but then there are intrusions, and that's something we're really interested in understanding. Okay, so with regional modeling, when you have a base simulation that you're, let's say, happy with, so you should validate against known observations, you can do a number of things. So you can change the sea ice cover and see how that affects the extreme weather events, changing sea surface temperature, or something I call a pseudo global warming technique. So essentially what you do is you take what global climate models are predicting in terms of ocean and atmospheric change, and you essentially downscale that and put that onto your simulation. So I use that technique to answer a couple of questions. So to what extent has climate change that's already happened contributed to the characteristics of cyclones that we see now? But then how will continued climate change and Arctic amplification affect cyclone behavior in the future? So I talked about this pseudo global warming technique. So from the CMIP6 large ensemble of lots of different models, we calculate a multi-model mean climatology of the historical climate, the current climate, and the future climate. And for the future, we do follow the most extreme of the socioeconomic possibilities. So we use these essentially to calculate deltas. So we have what is the historical delta, so difference between historical and now, and then the future delta, so now to the future. I've listed a lot of variables that we consider for a global warming scenario simulation. It's a big range, but these are all the variables that are needed in the boundary of regional models. So we are taking essentially as much as we can from the future climate or the change in the climate. So what we effectively do is for the historical simulation, we can effectively take away climate change that's happened to date and see how the cyclone responds. And we can add on future climate change to see how they'll respond in the future. We do change greenhouse gases in the model to be consistent with the atmosphere, but that's not strictly imperative at kind of these weekly timescales that we're talking about. Okay, I'll show you results from one simulation just for ease of viewing, but we did find consistent responses. So what I've mapped here is the sea ice concentration in the historical age. And then there's the changing tracks of the cyclone from the current simulation, which is the solid line, and the historical simulation, which is this dotted line, and then the future, which is the dashed line. We often see an increase in kind of the extent that the cyclones can track. So they kind of go further in their lifetime, and they also move faster, so they cover a lot more ground. We did find that the changes in trajectory were really governed by the large-scale flow in the atmosphere and how that's changing with climate change. So now I'm showing you a time series through the cyclone life cycle. So the sea ice concentration is in blue here, and the average surface temperature is in orange, and that's what's happening beneath the cyclone at every time step. So we only see kind of minor differences between the historical and current climate, but unsurprisingly, with the future climate change, cyclones travel over substantially reduced sea ice and higher surface temperatures. This is a huge change. And where I put the dotted lines is where sea ice concentration is less than 75% now. So you can see that's much more widespread in the future. So there is considerable warming throughout the atmosphere, but the surface is warming more than the upper levels. So this is driving really large changes in the temperature gradient between the surface and the near-surface atmosphere, with the atmosphere actually being cooler. So that's shown in dark red here. We see this huge change. This causes pretty dramatic changes in the surface turbulent fluxes on the right. So these large, really large positive values show that heat and moisture are being transferred from the surface into the atmosphere during the cyclones in the future. And with these sorts of models, they're convection permitting, so we're able to see that the surface and the atmosphere are supporting the development of CAPE, so that's the convective available potential energy and how cyclones can intensify. And it's actually something we see more in hurricanes than in like high latitude storms, but in the future we're seeing this factor even up here in the Arctic. So it's not traditionally induced at all in this region, but now we see that deep convection is possible. So yeah, the largest increases in the temperature differences and surface turbulent fluxes is really over areas where sea ice concentration is the lowest. So it really shows the importance of that sea ice loss and the kind of how the cyclones respond to that. So overall, the changes have meant that cyclone intensity is prolonged, so the time that is spent at maximum intensity. So lower SLP here, sea level pressure, means a more intense storm. But we also have notably enhanced wind speeds in blue, which are really significant for effects, local effects. So this is the one I've been showing you this whole time, but we have seen consistent changes throughout several cyclones that we've looked at. Okay. And yeah, so another effect that we see based on kind of future climate change is a really substantial change in precipitation. So this is actually showing augmented precipitation rates, but it's still falling as snow, so this kind of aqua color. And this is because we're still in March, so it is still kind of the end of the winter season. But this is actually really important because this could be a good thing, especially going into the melt season. If you're increasing the amount of snowfall on your sea ice pack, it could actually really help with sea ice survivability and that feedback we've been talking about a lot. But temperatures are creeping closer to this freezing line, so 0 degrees Celsius. And so once we cross that line, we would facilitate more mixed phase and liquid precipitation. And we do actually see a little bit of rain in the future scenario when we're close to this freezing line. But in certain cyclones, the future climate does push them above this freezing line. And so we do see a change in phase. And so now we see the presence of rain in blue, which doesn't exist in the current climate or the historical climate. And so we've talked about how rain causes melts and a decrease in the snowfall, the snow depth, and the sea ice. So, positives and negatives. I'll quickly touch on atmospheric rivers because this is a new piece of work that we're doing. So again, with these like flexible regional models, we had a different approach here. So we're running simulations where we just removed sea ice. So thinking about sea ice as this buffer between the ocean and the atmosphere, and when that only is changing, how does that affect atmospheric river characteristics? So if we zoom into the very small domain, these are the simulations where we reduced kind of the current sea ice concentration by 50% and 100%. And we're looking at the hourly total precipitable water through a simulation. So you can see that in the black line, so that's our current climate, but then as we remove sea ice, we increase the total amount of precipitable water. So the duration of the extreme nature is increased over the atmospheric rivers. And we're seeing a really large increase in the long wave downwelling radiation. So again, that can elicit a warming response. I think what we want to take away from this so far is that these changes are happening even when we reduce 50% of sea ice, and there's not even that much change then when you further get to 100% reduction in sea ice. So that's really important for thinking about kind of immediate changes and what we need to monitor and predict. This is very new work with my grad student at UMD. So we're using a Lagrangian framework, an algorithm that he developed to track the individual, filaments of water vapor transport. And so we can really in-depth analyze the evolution of each of the filaments and separate them from each other as well. This is a very new figure, but over the time of a 2-week simulation, we can begin to see shifts in the timing and duration of the tracked AR events. So the red is the events just in the current climate control simulation, but then when we remove 50% and 100% sea ice, the events are shown in like green and blues here. And also a preliminary analysis here is that when the sea ice is changed, we're seeing 2 more atmospheric events develop in the simulation compared to the current climate. So more to come on that. I will leave my summary here so that we have some time for questions. Yeah, thanks.
Thanks, Chelsea. People have questions? I'm going to let Chelsea build her own questions. She's a NASA fan. Can I ask you a question? How long is one of those, you're simulating these cyclones, just running a climate model with one cyclone, how long does it take to run before you even see the results? Like, how long does that take?
You mean the regional?
Yeah, or
Okay, so it depends obviously on how long the actual simulation, but let's say these this is a 2-week simulation with very high resolution, and it takes about 7 hours, which is quick in modeling standards. No. Takes 2 weeks to run 2 weeks. No, that's why we still need regional modeling, because global climate modeling is so computationally intensive, both in terms of like the actual computer resources, but the time it takes. So if we want to answer science questions and look at many different aspects and ways we can kind of ask the question, that's why we really need quicker models and more specific models.
I was wondering whether there are particular altitudes associated with, let's say, the formation of atmospheric rivers or cyclones.
Yeah, so on the base of it, so Arctic cyclones are really governed by baroclinicity. I don't know whether I should explain that or not. But so it's very much kind of the difference between, let's say, not the surface, but near surface levels and then the 500 millibar height and what's going on there. So baroclinicity essentially is a measure of how a cyclone is able to initiate and then intensify. So for cyclones, that's a really key parameter. But for atmospheric rivers, a lot of it is obviously about the global amount of water vapor, but then really the gradients from the mid-latitudes and tropics to the higher latitudes. And essentially the ability of our new kind of pattern of circulation to bring these up into the Arctic without just kind of raining out and dissipating first. Yeah. Yeah. So yes, for these kind of pan-Arctic things that I've been showing, it's very much satellite data. But thickness is very challenging. We have two different types of instruments. So we have LiDAR, which detects the top, just the surface atmosphere meeting point. But then our radar measurements are able to penetrate snow, so it measures the snow-ice interface. But both of those don't penetrate into the ocean. So we call what we can measure as freeboard. So that's the basically the bit we can see. Where's my freeboard? Yeah, so we can essentially measure freeboard, so this bit. And then we have to use, we have in situ measurements over the years. Obviously, they're like point measurements from buoys and ocean vessels and field campaigns essentially. So we have essentially now pretty established assumptions and hydrostatic equilibrium equations that go into sort of not guessing, but best guess calculation of the total thickness. So that is very challenging. And that's always the thing we say we need better measurements. Yeah. Yeah. Sorry. Oh, certainly. Yeah. Yeah. I mean, I'm obviously a NASA scientist, so then I would naturally direct you to several NASA resources, but there are also other really good sources that kind of, I've picked from them as well, and you kind of having these sorts of diagrams. But yeah, kind of walk through sea ice and how it's changing. Yeah.
Ages have come and gone. Would there have been similar cyclones and Arctic atmospheric rivers during the previous ice ages that we've experienced? And do you have ways of tapping into that far back historically?
So certainly these kinds of weather events have always and will always occur. So I think that's something we often try and talk about in climate scale and weather scale. It's that we always have weather, we always have climate, but it's kind of the rate of change that we're seeing now, which is completely unprecedented from ice ages. But they definitely would have occurred in some format throughout Earth's history. But I think one thing in terms of observations, it is very challenging. The longest records we have are ice cores, but that's primarily from ice that's on land. But you can tell things like what kind of weather would have been experienced by the snow layers and the thickness of different layers, and also when snow's falling, it has a lot of particles in it too, so you can tell stuff about like how the composition of the atmosphere back then. But with sea ice, is, you know, as we've seen, I mean, sea ice mostly melts out every year, and there's only multi-year ices at this point, maximum like 5 years. So that's obviously, you can't get long records from a sea ice core in that way.
So like we had Arctic, that was like kind of okay, but decreasing. And then we had this giant tipping point phase, the transition. Now we're like maybe stable again.
Yeah.
Maybe, yeah.
Until the next.
Still decreasing. Arctic bad. Still decreasing. But climate change real, Arctic bad. Is there a way to use these regional climate models or these climate models to be like, here's where we expect the next? Because in your future scenarios, right, you're like, there's no sea ice, this is bad, there's no feedback, it's going to be crazy storms, we're all going back to each other. But is there a way to be like, to put a number, be like, you know how some people are like, in the next whatever years, AMOP is gone or whatever,
Yeah.
like that sort of thing?
Yeah, we definitely can. And I'm working on a project that does that now. So when is the Arctic going to be ice-free? Yeah. And that means in the summer. So we don't expect sea ice to be gone in the winter in the future, but let's see. But yeah, so when is the Arctic summer going to be ice-free? And we can use what we have with global climate models and make those predictions, but we put range bars on it to say, like, I mean, I can't tell you it's going to be Monday. Monday, no, yeah. But I mean, we have a sense of that, definitely, especially the kind of like that broad scale. But I have been doing some analysis on kind of the scale of climate models for sea ice, and right now it suggests that they lose ice a little too quickly. So again, that would be the kind of thing where we would have some interpretation of that based on like our knowledge and understanding. Yeah. But yeah, you can make those predictions now. Yeah.
Have you been able to go to the Arctic and take field measurements?
So I am primarily a modeler, and second to that, a remote sensor. So neither of those things are in situ. It's still at my computer. But our lab at NASA, so Cryospheric Sciences, manages satellites that we have, and then we've also had airborne campaigns. So that means flying planes over the sea ice to take measurements. So that's the biggest opportunity for each of us to be able to go. And so we sit on the plane and we operate various instruments that look down on the sea ice. And also we help with planning flight routes and stuff like that based on sea ice and weather conditions. I haven't gone yet though.
I'd be interested to know, like, after you see the thing with your own eyes, like I can imagine a perspective changing or something that you will analyze in the future because you saw that edge or that, that one thing.
Yeah. That's, I think nothing beats seeing things in person and understanding the world around us. A lot of my co-workers have been, so I get a bit of that from them. Yeah. Yeah.
In class today, sustainability class, we were looking at maps of shipping routes connectivity. Of course, the Northwest Passage is a big argument among other passages in the north that are increasingly open due to the reduction in sea ice extent. And I was curious how you saw the intersection between potentially more traffic up there to the north, rather, and with these cyclones increasing in frequency, and just sort of a quick idea about the connection between, will there be more danger to those ships as we have an increase in the intensity and length of these Arctic cyclones?
Absolutely. So there's a lot of interest in sea ice retreat based on,
You said
Yeah, geopolitics. So you can just say it as transit, but other activities also. But I think you bring up a really good point, and that is why we also want to highlight changing weather. And yeah, we have the global climate signal and then what's superposed on that. So the things I've introduced, so polar lows and Arctic cyclones are known to cause extreme ship icing. So essentially like freezing water onto the ships, and that's a big deal and not good for the ships. But so I think it can be overlooked, especially by kind of the entities that are interested in the sea ice retreat. And there's this assumption that like warmer weather is better, but that's not how these extreme events operate. So I agree. They do pose like very extreme hazards. Yeah. Yep.
Did you mention what factors might have changed 2008, 2009?
Yeah, so I think there's a couple of things. The biggest thing is that essentially we have, okay, so yeah, so in the transition, we had this rapid loss. And so I tried to show, hopefully, that there was a really big feedback between, okay, the ocean warmed to a point, the ocean and the atmosphere warmed to a point that it thinned the ice and then it was susceptible to this melt. And then in the fact that it melted, it reduced the albedo, and so it can't reflect as much solar radiation, so everything just gets warmer, melts more, and it goes on. But what changed in this rapid transition is that we got to a point where we thinned the ice, and then we lost all this first year ice. So that's now first year ice melts out every year completely in the summer. That wasn't always the case, you can see back here. So this means that, yeah, first year ice could survive summer melt. So now we got to this point where it's not really a change anymore. We always melt out this first year ice, and we're left with this more stable multi-year ice. So that's essentially where like that kind of stopped the feedback for a little bit, in terms of like certainly albedo and things like that. And we also did see kind of clouds were a player here. It was like clouds are kind of acting on top of that a little bit, because we've seen an increase in cloud cover recently, which is kind of shielding some solar radiation. So that's kind of been helping. But yeah, I think the point that, yeah, I wanted to make was that, yeah, we're left with this multi-year ice, but it's thinning as well, given that we're still warming our climate. So you kind of get back, I'm basically trying to show that you could get back to a point here, well, let's say this is the multi-year ice now, and it's thinner and more vulnerable, and you can start that rapid change cycle again with the multi-year ice.
One more question and then I'll answer.
Mm-hmm.
Right? Oh, yeah.
So could it be that flat portion of the red graph is powerful as an explanatory thing for the stability of everything else we measure?
Right. Yes. Yeah. I think that was, yep.
Would you expect similar processes to be observable in the sun?
Yeah, I actually forgot to mention that. So I very much focus on the Arctic for this kind of big story, but I have two very similar works right now in review. So essentially looking at this same thing, but for the Southern Ocean sea ice. But it's interesting is that these are flipped. So we had seen very stable conditions, but now we're seeing a rapid transition in Antarctic sea ice.
They were in like a stable period for a longer time, and now.
So 2016 marked a shift in sea ice regime in the Southern Ocean. So the Southern Ocean is now in kind of that rapid transition phase. So I think that's also a really important point in terms of the global climate, because in a way, it was helping to maintain global albedo, and now that's declining too. And then I also have work on Antarctic atmospheric rivers and how they're changing.